papers primarily, which is coming with theoretical and numerical questions, apart from the other one which is on engineering drawing. Now, these two papers, particularly the one where in most of the states nowadays, you will see at least, depending upon state to state, 40, 50, 60% of the questions are based on numerical problem solvers, which are basically from thermal engineering. Now, one of the most important thing to understand or to learn to be able to solve the numerical problems is the measurement basics. So this tutorial is based on that. We are going to talk about some basics of physical measurement. See, if you want to measure something, any measurement, there are two things primarily. One will be the value, that is how much, 5, 6, 7, 8, the number, but it's not going to tell you we are talking about what. So there is another important thing, that is units, which is going to tell you what we are talking about, what physical quantity we are talking about. In terms of the importance, I can straight away tell you this way, that if you want to pass your examination, you need to learn the units very, very thoroughly. If you have captured the units, I would say you have almost done 60% of the job. So that is one thing we need to learn very thoroughly. So I'm going to cover this in this video tutorial. What you should do, first you should get a thick, large register, at least of 300 page or something, A4 size. Right? This register you keep for practice. Whatever you do, whatever preparation you do, you'll be doing in this register only. Now the first few pages of this register, you just set aside. You give a reference to this and go on taking some useful references. For example, I'll give you this relationship between different units. Also, I'll give you various useful informations like what is the value of NTP, STP, what is the value of, or what is the density of air at NTP and such. All this information would be very, very important and quite useful during the problem solving in the examination. You can have many of this. It is available in your study material, page A21 of chapter 1. So what you should do is you should start the reference with those informations, whatever is given in A21. And you go on adding to those references. Whenever you come across a particular information which you find it is important, you put it in the reference. That also includes the plant data of your boiler, which you know will be very much important for the Viva examination. So whatever the plant data, the boiler capacity, pressure, temperature, various readings in your system, all of those should go into the reference. The better, the big, the large, the more resourceful the reference is, the more chance you have for cracking this examination. It's as simple as that. Okay, now coming back to this units, you should know the relationship between various physical quantities also. In fact, if you want to, if you learn the units properly, you will become clear about that. For example, if I talk about power, as you know, is defined as is the rate of work done or rate of energy spent. So it's the relation between work and time, or energy and time. Now, if we talk about work we know is a multiplication of force into displacement, whereas force is measured as mass into acceleration. I can go ahead with this. Mass can be found out if you know the volume and the density by multiplying these two. You can find. So we know each and every physical quantity has got a relationship with other physical quantities. This is very important for us to know all this relationship and keep it in mind. It's not that you do not know, you have learned it during your engineering days. But one of the major problem, from our experience, I have found that with engineers like you who are right now as a profession, you are working somewhere. You have passed the academics quite a long time back, and therefore a lot of things have been forgotten. And that is one of the major reasons why we find it's very difficult to solve the numerical problems in this examination. So that's why I give very much importance to this particular subject or chapter. There is chapter 1. This is the basics of physical measurement. Okay, now you should also know the unit conversions, particularly from the MKS to SI system. You try to do everything in SI system only, or answer should be in SI system. But as the practice is there, we are using MKS quite often. For example, we use pressure as kg per centimeter square. We use the heat value of a fuel as kilocalorie, not kilojoule. So MKS is quite often used in the fill, but when you answer the BOE papers, those answers should be given in SI system. So we start with just a recapitulation of the units of various physical quantities. We'll start with MKS. For every physical quantity, we'll start with MKS system, and then we're going to take a look at the conversion of the SI system. Since SI system is a more I would say correct system, therefore the physical quantities, the relationship of different physical quantities are more it's clear in the SI system. There is not much ambiguities in the SI system. It's a very true system. So starting with this, let us say force. Before coming to forces, force is a multiplication of mass into acceleration. Let us start with mass first. Mass is kg in MKS or SI, irrespective of that. But the confusion starts when we talk about weight. Now, what is the unit of weight? We usually say, when somebody asks you how much your weight is, we say 70 kgs or 80 kgs or something. So answer is always in kg. But what is weight? Weight is not mass, it is actually the force. In fact, it is the gravitational force with which Earth is pulling an object towards its center. Right? The unit of weight is kg force. This is the unit of force in MKS system. Now, what is 1 kg force? 1 kg force is the force with which an object is pulled by the center of the Earth, which is having a mass of 1 kg. Right? So it is the gravitational force. So talking about force, we know force is mass into acceleration, and since this is a gravitational force, this is the acceleration is known, mass into g, mg. So when we say 1 kg force, mass is 1 kg, and the acceleration is g, which is 9.81 meter per second square. So it comes to 9.81 kg meter per second square. Now I'll point it here that it is very important to understand the kg meter per second square as a unit of force. This is the correct unit of force. In fact, in SI system, this unit is known as Newton. When we say Newton, every time it should come to your mind, we are talking about kg meter per second square. Whenever you multiply kg meter second and volume and such thing, always try to isolate kg meter per second square and replace it by Newton. You will find that your units will be much easier to understand. Right? So that is the unit of force. In MKS, it is kg force. Now, what is very, very typical, noticeable in terms of MKS system forces, you see 1 kg force and 1 kg mass. So mass and the force are both having the same value, that is 1 kg. So the value doesn't change, just the unit changes. It's kg for mass, kgf for force. In fact, in practice, we are not even using kgf. For example, when we say 9 kg per centimeter square, which is a pressure, this kg is not mass kg, it's a force kg. And we don't say 9 kgf per centimeter square. We say 9 kg per centimeter square. So in practice, it is basically where it is used. From there, we need to understand what we are talking about, whether it is mass or whether it is force. right? Okay. Now, talking about pressure, which is most important, and that is how we measure force. We do not measure force as it is, we measure it by pressure. And what is pressure? It is the force per unit area. If you see the pressure units, there are different pressure units. Most of the units are like force per area, but then there are other units like mmHg, mmWc. These are basically height of liquid column. So when we say pressure, pressure is not only force per unit area, it's also the height of liquid column, where we get the pressure equivalent pressure by H rho G. Okay, let's take a look at the different pressure units, conversion from the MKS to SI. Now, whenever we find the MKS system, I'll tell you one thing. If you see kg force, you want to convert it into Newton, what you do, you just multiply it in 9.81. It gets converted to Newton, right? So we convert this kg into Newton, centimeter square into meter square. So 9.81 on the numerator, 10 raised to minus 4 on the denominator. This 10 raised to minus 4 goes up, it becomes 10 raised to 4. So 9.81 to 10 raised to 4 Newton per meter square. If I want to make this 10 raised to 5, this will become 0.981. Why I want to make it 10 raised to 5? Because 10 raised to 5 Newton per meter square we also know as bar. Now this is a very, very useful relationship, the conversion of kg per centimeter square to bar. So whenever you see a unit of kg per centimeter square, you just multiply 0.981, you get bar. And if you have 1 bar, it's a vice versa, 1 by 0.981, that will be 1.0197. You can take 1.02 approximately as the conversion of bar to kg per centimeter. There are other conditions. One is the pressure, atmospheric pressure. Now this is also important to understand, because we are in the atmospheric system. Always this pressure is acting on us, and the standard atmospheric pressure, which is considered as the barometric pressure of 760 millimeter of Hg at mean sea level. Now you see, 760 millimeter of Hg denotes the height of a liquid column. Now how this is expressing the pressure? It is the equivalent pressure that is exerted by a liquid column of 760 millimeter, which is mercury. So there is a mercury column of height 760 millimeter. Now the pressure it is exerting at the bottom, let us consider the cross-sectional area as A meter square. Now this 0.76 meter height of mercury column is exerting a force at the bottom, which is due to its weight. Now if I want to find out the weight, that will be the force in MKS system, I need to find out the mass. Okay, and the mass is going to have the same value of the mass and the weight, only the unit is going to change. In order to find out the mass, I need to find out the volume and the density. And the volume I know, it's already, the height is given as 0.76 meter and the cross-sectional area is A, so it's 0.76 A meters cube. And the density of mercury, we can assume, or we used to assume, in fact this is one thing you should put in the reference, as 13,600 kg per meter cube. Not 13.6, mind you, 13.6 is the specific gravity of mercury. Specific gravity is the relative density of any substance as compared to water, which has got a density of 10,000 kg per meter cube. Now, if I multiply the volume into density, I get a mass of 10336 A kg, right? Now, this mass will be acting a similar force of 10336 A kg force at the bottom over an area of A meter square. Therefore, the pressure, if I find out as force per area, that will be 10336 kg per meter square. Now, this kg per meter square is a very, very useful pressure unit for BOE examination. We do not use it in practice. We use kg per centimeter square, right? But kg per meter square, please remember, is a very useful unit in BOE examination. Now, if I want to find out or convert the pressure of a height of a liquid column into kg per meter square, what I have done, if you see, I have taken the height and I have multiplied it with area. So to get the volume, then I multiply it with density, right, to get the mass. The mass will have the same force as weight going down, overacting over a cross-sectional area of A. Now A gets cancelled, so it remains as H into rho. So it tells you a pressure equation. If you know the height of a liquid column, the equivalent pressure is H into rho kg per meter square. And if you multiply it with G, kg will become Newton. This will become Newton per meter square, which you know as Pascal, right? So 10336 kg per meter square will be 1.033 kg per centimeter square. And 0.981 tons, if you see, it will be 1.013 bar. Now, again, there is another relationship, this is also very important, that since 760 mm of Hg is equal to 1.013 bar, 1 bar will be equal to 1 by 1.013 will be 750 mm Hg. Now, this relationship is quite often required, particularly when you are going to do the condenser calculations. It will be very much used. Okay. Now, liquid head, as I have just discussed, is H into rho kg per meter square, where H is in meter and kg per meter cube is the density. Now, if you take 1 mmWc, right, 1 millimeter water column, where the H height is 0.001 meter, and the density of water is 1000 kg per meter cube. Therefore, 1 millimeter water column will come to 1 kg per meter square. So, you see, when you say mmWc, we are talking about kg per meter square, both are same. Please remember this is going to be very useful for your examination. If you see kg per meter square, it is either kg per meter square you can write, or 10 raised to minus 4 kg per centimeter square, or it is 1 mmWc. And similarly, if I understand 1 kg per centimeter square, it will be 10 raised to 4 mmWc. And that's why, you know, in the field also, we take 10 meter of water column as 1 kg per centimeter square. Then comes the understanding of absolute pressure. What is absolute pressure? Usually whenever I ask this question, the answer usually comes as absolute pressure is the gauge pressure plus atmospheric pressure. But that is how you are calculating absolute pressure, and that too is not correct all the time. Absolute pressure is the actual pressure in the system. If you see a system like this, let us assume a closed system, a drum is filled with steam or some other gas which is exerting a pressure, right? Now let us assume the pressure is 10 kg per centimeter square. Every centimeter square area is exerting a pressure force of 10 kg force. Let us, for the simplicity, assume the atmospheric pressure is 1 kg per centimeter square instead of 1.033. Now what is going to be the gauge reading? If I take a pressure gauge, what is going to be the reading? Will it be 10? Will it be 11 or will it be 9? Now this is the understanding, is the gauge pressure is never giving you the actual pressure. The gauge pressure will be 9 kg per centimeter square, and you can see it is the difference between the actual pressure and the atmospheric pressure. You see, whenever the gauge is there, it is always under the atmospheric pressure. It cannot sense the pressure unless the pressure becomes more than atmospheric. And when it becomes more than atmospheric, it can only read the difference of the pressure. So gauge pressure is the differential pressure. In case of a pressure gauge, that is the pressure is, if you see, you understand it better way, when you, at the starting of the boiler, when you just start, you take the normal drum level, you do not put heat, therefore there is no steam inside. What is the pressure inside? The pressure is same as atmospheric pressure, which is, let us say, 1 kg. And the gauge is going to give you a 0 reading at that time, because that is reading only the differential pressure, right? So if it is a vacuum gauge, now that's why I told you that gauge, absolute is gauge pressure plus atmospheric pressure may not be correct all the time. If it's a vacuum gauge, then the pressure inside is less than atmospheric, and this gauge is showing the difference. Therefore, to get the actual pressure, you have to actually deduct the gauge pressure from the atmospheric pressure. Please remember this during the condenser calculations. Any calculation, you must first calculate the actual pressure. If the gauge pressure is given, you do not go with the gauge pressure, you calculate the actual pressure inside the system, right? Now there is one more pressure unit, and that is ETA. Excuse me. Now what is ETA? ETA, the use of ETA is not so frequently been seen these days, but ETA is nothing but a scale in the kg per centimeter square unit, right? It's 1 ETA is 1 kg per centimeter square. Only difference is we are talking about the absolute pressure. So 1 ETA is 1 kg per centimeter square absolute, right? In this case, if I talk about what is the pressure, this should be 1 ETA pressure here, right? If I take an ETA gauge here, it is going to show you 1 ETA. Okay, now I should point it out that whenever you come across pressure, it is not going to be a bad idea to convert the pressure into kilopascal. Every time you do that, you have a chance of making less mistakes. So you should know the conversion of all the pressure units to kPa, right? So in your reference, you should write it down, okay? And you memorize. Whatever you write down in the reference, you memorize. That is going to help you a lot. So starting with, let us say, what is kPa, kilopascal? If I see the relation between bar and kilopascal, 1 bar is equal to 100 kilopascal. Okay, and in fact, when you try to convert the pressure units, I would suggest that you convert it through bar. You come via bar. For example, let us say 1 kg per centimeter square. You convert into bar. We know that multiplying it with 0.981 is going to give me bar. And if I get 1 bar, then multiplied by 100 will give me kilopascal. So 1 kg per centimeter square will be 1 into 0.981 into 100 kilopascal. If I take mmH, okay, how do I convert into bar? I've just shown you earlier, which you have to remember afterwards, that 1 millimeter of Hg, we know 750 millimeter of Hg is 1 bar. So this divided by 750 will give me bar, multiplied by 100 will give me kilopascal. mmWc. Now what is mmWc? As I told you, whenever you see mmWc, the first thing that should come to your mind, it is kg per meter square. So when it's kg per meter square, I know if I multiply 9.81, I can convert kg into Newton, right? So I multiply 9.81, I get Newton per meter square, that is Pascal. So 10 raised to minus 3 of that will be giving me kilopascal. Okay? ETA. I told you, ETA is same as kg per centimeter square. So whatever I used for kg per centimeter square, same will be used for ETA. Only difference is, this time the kilopascal pressure will be the absolute pressure which I am going to get. Then there is another unit which is not used for pressure so much, rather it is more used for the stress measurement. That is Newton per millimeter square. Newton per millimeter square, if you convert it into Newton per meter square, you will get 10 raised to 6. That means it's 1 Newton per millimeter square is actually 1 megapascal. And if it is 1 megapascal, then it is 1000 kilopascal. Right? So similarly, you should have in this written in the reference and memorized. Okay. Now there's an example. Just let us take a look how to solve these examples. This is using the different units relationship. A manometer joined to a gas cylinder indicates 20 kPa, while the barometer reads 760 mm of mercury. Now, please remember, if the barometer reading is given, you take the barometer reading. If it is given 750, you have to take atmosphere as 750 mmH. If it is not given, then you can assume the standard barometric pressure. Here it is given 760, so there is no issue. What will be the reading of the manometer if the barometric pressure drops to 730 millimeter of mercury? Now, what you do, how you do, okay? The first thing you should do is conceptualize. It's not a bad idea to just draw a little diagram on your paper. Okay, so this is the cylinder which is connected to a manometer. We know how a manometer looks, which is open to atmosphere. It is filled with either mercury or water or whatever the measurement liquid is, and this pressure is more than the atmospheric pressure. Therefore, the liquid is going to push up. Right now, if I just take a look at this, that the manometer pressure is the differential pressure between the atmospheric pressure and the actual pressure, right? What is important is that the barometric pressure may change, but going to change in this case? So if the manometric pressure changes and this doesn't changes, what is going to change is this differential reading, right? So we know the manometric differential reading is what? It is the P absolute minus this 760 millimeter of Hg. That is 20 kPa that has been given, right? So P absolute minus 760 mm of Hg is 20 kPa. Now this is changing. This is changing by 30 millimeter of Hg, right? So this goes down. Naturally, this goes up. So this minus 730 will be 20 kPa plus 30 mm of Hg. All I need to do is now convert the mm of Hg into kPa, which is done by 750 multiplied by 100, right? So divide by 750 will give me bar, multiplied by 100 will give me kilopascal. So the answer will come to 24 kilopascal. It was easy, isn't it? Okay, now go ahead with this way. Let's come to work. Okay, finish this. Now, work is force into displacement. Work is also pressure into volume. We do not measure force, we measure pressure, and force into area is pressure. Force divided by area is pressure. Therefore, if I replace force by pressure, it will be pressure into area, and area into displacement will give me volume. Now, in terms of unit, as I told you, starting with MKS, force kgf, displacement meter. So kg meter is the unit of work in MKS system. If I want to convert it to SI, kg I multiply by 9.81, I get Newton meter. And Newton meter is known as joule, right? So mostly we get across kilojoule, not joule. Joule is a very small one. So kilojoule is nothing but kilonewton meter, right? Okay. Talking about energy. Okay. Now one thing is important to remember, that if I am finding out the work in kilojoule and if I am using this PV as the equation of work, where the volume will be in meter cube, the pressure will be always in kPa. Please remember this. You cannot take any other pressure unit if the work is in kilojoule and the pressure has to be taken in kilopascal, right? That has to be remembered. We're talking about energy. It's capacity of doing work. Same as work, the unit will be same in SI system. In MKS it's different, and that is why SI is more scientific unit. We know that the energy is primarily of two types in macroscopic form. It is kinetic energy and the potential energy. Kinetic energy also, is denoted by half mv square and potential energy with mgh. And in fact, that is one of the reasons why whenever we talk about potential energy, we look for something which is located at some elevation. And for kinetic energy, we look for something which is having some velocity. That might not be the case all the time. For example, the most important form of kinetic energy in boiler engineering is the heat energy. That is a form of kinetic energy. And the calorific value of the fuel is a potential energy. Okay, talking about heat energy, this is the most important energy for us. So let us find out how to assess the heat energy. There are primarily two forms of heat energy that is available in boiler system. Okay, one is the sensible heat. Sensible heat is the one where you heat it, the temperature goes up, right? That's, you can sense it. Another is the latent heat, which is you put when there is a change of phase from solid to liquid, from liquid to gaseous. Primarily for us it will be from water to vapor form. Now, the sensible heat, please remember, is very easy to assess, very easy to measure. What you need? You need the mass, the temperature difference because of addition or deletion of the heat, and the specific heat characteristics of that substance. It's a constant. And this is calculated as H is equal to mc delta T. Please remember this as a Gayatri mantra of heat energy system, right? Anytime we want to measure heat energy, if it's sensibly, H is equal to mc delta T. That would be all. Here, the specific heat is a constant which changes from matter to matter. So few specific heats are required to be known by us, namely I'll give you a list of that. The latent heat, you can always calculate from the steam table. In fact, during my video tutorial on steam, properties of steam, I'm going to cover this. You need to remember some specific heats. So this is given in the reference. You can also write it down in the reference, right? Water, you can assume as 1 kilocalorie. Steam as half of that. Gas, air, you can take both as 0.24 kilocalorie, but one is 0.24, another is 0.23. And you may also need the specific heat of ash, particularly in terms of coal-fired boiler, which is taken as 0.2 kilocalorie. Okay. Now, let's see an example where the MC delta T idea is, or rather the relationship has been used. The inlet and outlet of the air side temperature across the air preheater are 35 and 240 degrees centigrade. The mass of airflow and gas flow are 650 and 608 TPA stands per hour. Calculate the air preheater outlet gas temperature in degrees centigrade if the inlet temperature is 350. They have also given the specific heat of air and gas. So first thing we need to find out, okay, what is we are talking about. So this is, we are talking about an air preheater, air heat exchanger, where there is an air coming this way or there is a gas going this way. Now just note down on the paper the data which has been provided by you. Okay, that is going to, make it from this writing to some specific data like this. Okay, so what has been given? They have given you the air temperature in and out both. They have given you the mass of air, mass of gas. They have also given you the gas temperature of inlet, and they have given you the specific heats, right? So the gas air is 650 tons per hour with 35 degree inlet and 240 degree outlet. The gas is 608 tons per hour with 350 inlet. The outlet is not known to us. Okay, so this air is losing, gaining heat, and this gas is losing heat. Okay, now the heat lost by the gas, if I say M, I know delta T is 350 minus T, and the C is given. So the heat lost by the gas is MC delta T. We can find out in equation like this. And the heat gained by the air is again MC delta T. Which is coming to this. Okay. Now what we need to assume is there is no loss in between, and heat gained by the air is heat lost by the gas. And if we equate this, we can easily find out as the temperature. Right. So there this is a very simple example, and similar examples are given. We do it like this, it becomes very simple for us. So what you do is you put a diagram, you put all the data on your paper like this, and then you will see that the total example, no matter how large it looks, it will become very simple to you. In BOE examination, that is one of the tips I can give you, that nothing is rocket science. Everything is very, very simple. Just put it in paper, think it simply, you will be able to solve it. Okay? Let's go on to power. Power is work per time, that is rate of work done, or energy per time. Now here, if I go to the unit, work is, we remember from MCAS system is kg meter. So it will be kg meter per second will be the work unit, power unit in MCAS system. And in case of SI system, I can convert it into, with 9.81, it will become Newton meter, that is joule per second, and joule per second is watt. Please remember, whenever you see watt, you will always read it as joule per second. Now this is another tip I can give you for BOE examination. Never see watt as watt. Always see watt as joule per second. A lot of your problems will be solved. Okay. Now there are some other units as well in power which are being used, and that is one of them is H, horsepower. Now please remember there are two horsepower, so two different types of horsepowers. Those are used in system in engineering field. One is a metric HP or metric horsepower, which is equivalent to 75 kg meter, because kg meter per second is the unit of power in MCAS system. So 75 kg meter per second. If I multiply it with 9.81, this will become Newton. So this will become watt. It comes to 735.75. But the one which is being used in the field is the British horsepower, and that is 33,000 foot-pound per minute. If I convert foot and pound and minute into SI system, meter, kg and second, I will get 746 watts. Please remember, in BOE examination, not in all states, but wherever they are asking in HP, they mean the metric HP. Okay, in the field it is the British HP, but in BOE examination, in theoretical paper, it is the metric HP that is being used. But most likely the HP is not will not come here. If it is coming, it's not going to be a bad idea just to assume that, assuming the HP as British HP or metric HP, whatever you want, you can just write down assuming the HP given as that. Okay, please remember there are two different HPs, so just sort this out. Now, talking about this equations, F into D by T is power, P into V by T is power, because PV is watt, and V by T is the volumetric rate of flow, that is the discharge Q. Now, this P into Q is a very, very useful equation, quite often being used, primarily to find out the power of the fans and the pumps and such. Whenever there is a prime mover, it's creating a flow against a pressure. When you multiply the pressure with the discharge, you are going to get the power, right? And if you want to find out the power in kilowatt, do not forget to take the pressure in kilopascal, otherwise the answer will be wrong. Okay, that's why I told you that the kilopascal is the most useful unit in pressure unit so far as BOE calculations are concerned. Okay, so the volumetric discharge will be in meter cube per second, the pressure will be in kilopascal, right? Okay, now let us say if I talk about the pump, okay, now in the pump, which is being powered by a motor, the shaft is moved by a motor, and the motor is getting a power from the source. Now there are, one is the source power, another is the motor output, and another is the pump output or fan output. Now this output of this pump or fan is known as hydraulic power. Please remember, when we say pump power, it is the hydraulic power we are talking about. But then there is a input to the pump, which is the output of the motor. This is known as shaft power. This is not the motor power. Please remember that. In the field, when we say motor power, it is the motor output. Okay, rated output of the motor, but not in the BOE examination. In the BOE examination, this is the shaft power. The motor power is the source power. That is the motor power. That is the consumption. Okay. Now, the relationship is what? If I want to find out the efficiency of the pump will be hydraulic powered by shaft power. If I want to find out the efficiency of the motor will be shaft powered by motor power and such, right? Output by input. An example, let's take a look. But before that, you must also keep it in mind that what pressure we are talking about. Suppose there is a discharge pressure is given, we should also see whether a suction pressure is given as well or not. Because if there is a suction pressure given to the pump, then the net pressure against which it is creating the flow will change. For example, if you take a look at this. If the suction is above the pump center line, that means even if the pump is not there, this much head will be attained by this liquid head itself, right? So that means that much head is not required to be created. In such cases, the net pressure will be HD minus HS. But on the contrary, if the suction is below the center line, that means not only this discharge head, this much head is also to be created by the pump. It has to be sucked by the pump. Then the net pressure will be HD plus HS, right? So that has to be remembered. And H rho G is the pressure in Pascal, and 10 to minus 3 will make it kilopascal, multiplied by Q in meter cube per second will give you the power in kilowatt. Let us quickly take a look at the example on similar one. Okay. Now in this example, the suction of a pump is given 5 meters below the pump center line. The discharge pressure is given as 3 kg per centimeter square. The flow rate is given in meter cube per hour. They have asked us to find out the pump. Given you the actual power input to the shaft, that is the shaft power, that's 12 kilowatt. So let us first draw the pump. Okay, and the suction is below the pump set line, therefore we know that it has to be added, right? Now the data which they have given, we can just write it down one by one. The suction head is given as minus 5 meter, that is below the center line. The discharge head is given as 3 kg per centimeter square. We know that every kg per centimeter square in terms of meter of water head, it is 10 meters. So 3 kg will come to 30 meters. The discharge is given as meter cube. Again, the shaft power is given. Mechanical efficiency is hydraulic power by shaft power. If I use the equation, put the value of HD, HS and Q, I get the value of hydraulic power as 9.54 kilowatt. Therefore, the mechanical efficiency is hydraulic power by shaft power, which is coming to 79.5%. Now, this is how we should solve the numerical problems given in BOE examination. Take it step by step. Put a diagram, put the values on paper, then the question will become pretty simple to you. Now, I think that would be all for this video tutorial. In my next tutorial, I'm going to talk about the gas laws. Now, this gas laws chapter will be very, very important because the combustion calculation, which is one of the most important calculations in BOE examination, is based on the gas laws. Rather, the gas laws fundamental understanding will be absolutely essential in order to solve the combustion problems. Okay. Meanwhile, what you should do is you should read the chapters and you should try to practice with the relevant questions which I have covered so far from the chapter number 1, that is, right? And what is very, very important is you should memorize whatever that is given in the page A21, which I asked you to put in the reference, right? The faster you memorize, the better it will be, or the easier it will be for the preparation of BOE examination. With that, I should say thank you.